Hello, hello. Gonna do the questions for section 6.2. So I have a couple of questions that I want to go over. I'm gonna go over all three sections. It's 6.2D, 6.2CI, and 6.2HT. They all seem to me to fit together. And I have up on the screen the formulas here that apply in this section. I'm reminding you again that there's this page in the book. I'm gonna flip to it. So page 478 that has all the formulas, including the ones that are here, and so they're all gathered together in one place. A person can feel like they don't need to go hunting back through the book. It's all right there on one page. And the key thing with these is that it involves a T. You use a T in the context where you do not know the standard deviation of the one at a time numbers. Remember, the SAT company publishes that the standard deviation of the math SAT tests, the many thousands of hundreds of thousands of people take the math SAT test, they found the standard deviation of all that huge population, and they publish it it's 100. But if you don't know the standard deviation of those numbers, and that's a very typical case, if you don't know the standard deviation of that numbers, you have to instead get by using the standard deviation of your sample, S. Well, then you have two things that you don't know. You don't know the mean, but you also don't know the standard deviation. So you're in a situation where you know a little less than we have previously in this course. So the twist in this section, in finding confidence intervals in a hypothesis test for means, the twist in this section is that we have to use a different place on stat key. It's called the T curve. That's why this says a T, and this says a T, and of course we're going to practice with a couple of them. Okay, let's start in with the first one then. Let me bring up the book. And I'm going to do question 64. Let me find the darn thing, question 64. My goodness, it doesn't look like it's in very good focus. Anyway, it's just a question out of the book, and a person can read it out of the book. It says, if random samples of the given size are drawn from a population given mean and standard deviation, find the standard error, so that's the spreadedness, find the standard error of the distribution of sample means. In other words, the sampling distribution, the thing that you're so interested in, for example, in a hypothesis test, find the spreadedness. Okay, and question 64 says samples of size 10 from a population with mean 6 and standard deviation 2. Okay, so bring out my piece of paper. All right, so it says samples of size 10. So we're interested in the sampling distribution. The sampling distribution, and those always look like so. They're usually narrower than the underlying population, so I make them look, I know it's a little ridiculous, it looks ridiculously narrow, but it helps me to remember. And they're always going to be, if it's a sampling distribution of X bars, then we know how to calculate the spreadedness. The formula that we were just looking at 30 seconds ago says the spreadedness, remember you find the place where the curve changes from umbrella shape to bowl shape, and that's about here. This distance right here is sigma over square root of n, where sigma is the standard deviation of the population and n is the sample size. So reading question 64 again, it says the samples of size 10, so n equals 10, from a population with mean 6. It says population, not sample, population with mean 6. And then it says standard deviation 2. So this is a population standard deviation, not a sample standard deviation, population standard. So I'm writing down what they told me. Okay, and then of course they just simply want me to find sigma over square root of 2. That's, sigma over square root of n. So that's 2 over the square root of 10. And I don't know what that is, of course. My calculator knows what that is. Oh, I hit it way the heck over here. Okay, so 2 over the square root of 10. 2 divided by square root of 10. And my calculator says 0.63. So that spreadedness, that distance right there, is about 0.63. Okay, so that was number 64. Next one I wanted to do is 84. That's a confidence interval question. Find the darn thing. There it is. Ah! Making a mess of things. There we go. Okay, 84. 84. It says give me a 90% confidence interval for mu. So this is section 6.2. It's on finding the mean. So that says a 90% confidence interval for mu. Using sample results, X bar is 137.0, S is 53.9, and N is 50. And it's hard to read. I'm sorry, the camera for some reason doesn't focus all the time. So I'll write these things down. This is number 84. And they want a 90% confidence interval. And they tell me you're supposed to use O for mu. That's why we're in section 6.2, because we're worried about means. In section 6.1 we were worried about proportions. Here we're worried about means. Okay, then it says X bar is 137. S is 53.9. And N is 50. Okay, and again, just to try to speak globally here, exactly what's happening here is that this is not sigma. This is not the spreadedness of the population. We happen not to know that. We often don't know it. You know, if you give, let's say you give rats cocaine and you have them run through a maze, well, who knows what the spreadedness of rats with cocaine running through a maze is? So you don't know that. In addition to not knowing the average, you also don't know the standard deviation. And that's just a situation you often find yourself in. So what do we do in that context? We know less than we're used to knowing. We not only don't know the mean, we also don't know the standard deviation. Okay, so you have to use this t-curve thing. So let's see, the formula from the slide that I just popped over here is x bar plus and minus t star by s over radical n. And the s is right there, the n is right there, the x bar is right there. It's this t star that I have to find. So you have to look up on the t curve. I'm looking on the t curve because I don't know the spreadedness of the underlying population. So I have to make do with the spreadedness of the sample. Okay, so I'm looking it up on the t curve. Let me pop that thing up if I can remember how to work all this stuff. There we go, there's stat key. So I'm looking here and finding, oh no, I got to get it out from behind my thing there. Okay, I'm looking here and I'm finding the t on the t curve. Good. And now this part's a little weird, I have to confess. So there's perfectly good, sensible, theoretical reason for it, but basically you take n equals 50 in this context and you write in 49. So you always subtract 1, so 49. I don't know why I thought I wanted 55. Anyway, you enter 49. Okay, and you get a curve that looks an awful lot like a normal curve. It turns out it's not exactly the same, doesn't follow the same formula that I gave you a long time ago for a normal curve. It's a little shorter in the middle and a little taller at each end. So this is a t curve. See the t over there? This is a t curve. And what do I want? I want a confidence interval for 90% confidence interval. So I want to know, what do I use when I want the middle to be 90%? So make the middle be 0.90, 0.90. And if this was a normal curve, I would have used 1.645. But it's not a normal curve. It's a little different. It's somewhat changed shape. And so instead of 1.645, I need 1.677. A small difference to be sure, but an important one. So 1.677. I got that by finding the 90% middle. And don't forget that I did degrees of freedom equals 49. So 1.677. Let me get rid of this thing here. There we go. 1.677, 1.677. Write it down real fast before I forget it. Plug in the S, plug in the N, plug in the X bar, hit a calculator, and you're done. Okay, so S is what, 53.9, square root of 50. And X bar is 137. And I'll calculate it. But we're basically done, aren't we? Because nobody in the room ever raises their hand and says, I can't work a calculator. That never happens. Okay, so let's see, 53.9. I keep saying nobody in the room. There's no room. It's a little weird, isn't it? Divided by the square root of 50 equals, multiply times 1.6 1.677 equals, oh, I said 1.67. I better do the whole thing again. So let's see, 53.9 divided by square root of 50 equals, multiply by 1.677, 0.677 equals 1.278, so I'll round that to 1.28, and so I got 12.78, so 137.0 plus and minus 12.78. And again, this a confidence interval, I'm going to find both ends, but at this point, we're done. You have to still punch buttons, but at this point, we're basically done. Okay, so 137.0 plus 12.78. That gives me the upper end, 149.78, and the lower end is 137 minus 12.78, 124.22. 124.22. Okay, and again, as always with a confidence interval, getting the answer is good. It's good to get the right answer. But the most important thing is to understand what a confidence interval is about. This does not tell us where the x bars are. Confidence intervals are not about x bars. Confidence intervals are about the population number. Confidence intervals are about mu. We are pretty sure that mu lies between these two numbers. So in summary, again, we use t. If you were doing a bunch of problems and they were all spread out, or maybe you're working on a assignment for economics and you have to figure out which formula to use on your own. Why did we use the t? And the answer is because we're looking for means. Right there, looking for means. And we do not know the standard deviation of the one at a time numbers. We have to get by with the standard deviation of the sample. So there are two things that we're somewhat unsure about. We're somewhat unsure about the true average, and we're somewhat unsure about the true standard deviation. So in that context, you have to use the t-curve. Okay, but confidence interval means the same thing. It tells you where mu is. That's what a confidence interval is about. Okay, that was 84. I also want to do 92. 92 is a word problem. It's the only difference between 84 and 92. Let's see if I can sneak it over here. 92. Okay. Get it under the screen. 6.92. It doesn't really fit on my desk so well. So in addition to being hard to read, it doesn't fit on my desk. It says, how much TV do college students watch? 361 students recorded the number of hours of television they watch per week. Average is x bar equals 6.504 with standard deviation of 5.584. And you'll notice that it doesn't say sigma equals, it doesn't say s equals. They expect you to figure out that this must be the sample standard deviation. Because how would you know the spreadiness of how much television all college students watch across the country? You wouldn't know. You'd have to go with your sample number as your best guess to the spreadiness. In that context, when you're going with a guess about the spreadiness, why you have to use the t-curve. Okay, find a 99% confidence interval for mu, and then it says interpret the interval in context. Okay, so let's see. So I'm looking here at 99% confidence interval for mu, and I'm told that x bar is 6.504, that s is 5.584, and that n is 361. Okay, 361. So once again, if you were doing this problem in political science and you weren't in this section 6.2 and knew you had to use the section 6.2 formulas, how would you know? And the answer is this S is the giveaway. We are working with not only not knowing the mean, but we also don't know the spreadiness of the underlying population. We are trying to figure out where does mu lie in a context where there are two different things we don't know. That's why we're using the t-curve. Okay, well, of course, the formula is right over there. So it's x bar plus and minus t star by s over radical n. My handwriting is so embarrassing. S over radical n. So that's 6.504 plus and minus, I'll leave the t star blank for a second, and I'll bring up stat key and it will tell me the answer, 5.584 over square root of 361. I'll figure that out by bringing up stat key. So where's my stat key button? Aha, I found it, first try. Okay, there we go. There we go, okay. I lost it over here. There we go. Okay, this is the previous problem, of course. Now I want a 99% confidence interval, but not only that, I got to be careful. It's a different degree of freedom. So you can edit the parameters, and I'm going to do that. But you can also always go back to the beginning here and say t equals, and it'll come up and ask you. So that's a tip, is that if you're using the t distribution twice in a row, be careful. You got to change the degrees of freedom. Here, n is 361, so I'm going to enter 360. So 360. So be careful. I mean, I've seen people, that's a, you say to yourself, oh, what was I thinking? What was I thinking? Another place you can change the same thing is here, edit parameters. It allows you to enter it there. Okay, I want a 99% confidence interval, so I want to know what number to use when the middle is 99. So you click on two-tail and click on 95. And don't enter 99, enter 0.99. I can't tell you how many times I have done that. If this was a z curve, if this was a normal curve, I'd of course be doing 2.576. Here it is 2.589, so pretty close, pretty close. A little bigger, but still pretty close. 2.589, so let me get rid of this and go back to my paper. So this is 2.589, 2.589. Okay, and the warning is, don't forget to change the degrees of freedom. You take n and subtract 1 from it. No, I'm not gonna bother you folks with manipulating the calculator. Everybody in the room can do a calculator. So we'll get a confidence interval, and as I remarked over here, the confidence interval tells us not where x bar is, or future x bars, or where the individual numbers are. None of those things. What the confidence interval tells you is where mu is. We are pretty sure, pretty darn sure, that mu is somewhere in this interval. Okay, last one I want to do is number 118, if I find it. So 118 is on page 435. Bring it up here. Here we go. And 118 is a straightforward hypothesis test. It says test H naught, which is mu. Oh, the person can hardly read that at all. Darn this camera. Oh, I bumped it earlier. That's what happened to it. Test mu equals 4 versus HA. Mu is unequal to 4, so it's a two-sided test using the sample results, and I'll write all this down on a piece of paper where a person can read it. So number 118, 6.118 is I've got to test H or naught, which is mu equals 4, against HA. Mu is unequal to 4. And the data that I have to do the argument with is x bar equals 4.8. So it's some distance from 4. Is it far enough? We'll see. S is 2.3. And N is 15. Okay, and once again, trying to make the point, we are going to use a T curve. I'm going to go to the T place on that key precisely because this says S. Not only do I not know the mean, I'm arguing about the mean here. Not only do I not know things about the mean, but I also don't know the standard deviation, so that calls for a T curve. Okay, hypothesis test. What was the first 2 words in hypothesis? Always assume H naught. Okay, so a familiar signpost, you always say assume H naught. And then the sampling distribution, the distribution of x bars is, and you get a curve that looks like this. The H0 people tell me that mu is 4, tell me that they think the true number is 4. Of course, we think it's not, but they think the true number is 4. So they think then that the samples would be centered around 4. And they think that the spreadedness would be S over square root of n, which is 2.3 over square root of 15. And let's see what my calculator thinks that is. 2.3 divided by square root of 15. Ah, darn it. 2.3 divided by square root of 15. 0.59, 0.59, 0.59. So it goes up a little more than a half, and a little more than 1 would take you out to 2 standard deviations, and then down to the other side 2 standard deviations. Okay, and we have a sample of 4.8. We want to know is 4.8 so far from the middle that it convinces us that believing this is not really very sensible. Okay, let's see. So find the p-value. So I'm trying to draw exactly the same curve. It's embarrassing, isn't it? And I want to find where is 4.8. Is it a way off crazy sample, or is it perfectly possible? Don't forget though, this is a two-sided. So I got to test not just something that is 0.8 above the mean, but I also got to go for 0.8 below. That is to say, because this says unequal, I got to shade an area on the right and also shade an area on the left. The area on the right is 0.8 above the middle, so I got to shade the area that is 0.8 below the middle, and that's going to be 3.2. And of course, the p-value is going to be the total. So I never figure these things out. I always ask Zaki, what is this? The thing is that because that's an S, I am going to look it up on the T curve. So I will ask StatKey for that area by looking it up on the T curve. Okay, so let's see, bring up StatKey, see what we get. There's StatKey. The warning that I gave you last time still applies. It's very easy to forget to change that number. The sample size here is 15, so I got to change it away from 360, what it was in the last problem, and change it over to not 15, but 14. 14. Okay. And again, it looks a lot like a normal curve, but it's slightly different, a little smaller on the top, a little bigger on the edges. Anyway, it's a little different. So I got to figure out where is my sample 4.8 on this curve. So I'll figure out what is the T location of 4.8, and then I'll shade that area, and then I'll just double it. So I figure out what is the T location. On the normal curve it's a Z location, but here I'll figure out what is the T location for that, for 4.8, and then I'll find the associated area and just double it. Okay, so I'll calculate the T location. T equals 4.8 minus 4.0, that's telling me how far it is, divided by 0.59. So is it 2 standard units or 1.5 standard units, or what the heck is it? So 4.8 minus 4.0 divided by 0.59. 4.8 minus 4.0 equals, divided by 0.59 equals. Oh, what do you mean syntax error? Don't give me that. So 0.8 divided by 0.59 equals, oh, I wonder what I did wrong. Anyway, it says 1.36. 1.36. So I'm going to go back to the T curve, enter 1.36, and find the associated value. So here we go. Here we go. Come on. There we go. Well, I'm looking for a right tail, and I'm entering 1.36. 1.36, and I get 0.098, but that's only half of the region I want. I want to double it. I'll take that and the other area too. So 2 times 0.098. Let me get rid of stat key here. 2 times 0.098. So the p-value is, I did the upper was 0.098. Don't forget the lower. 2 times 0.098. and I don't know what my calculator thinks it is. So 2 times 0.098, and my calculator says 0.196. So that's about 20%. So more than 19%, it's about 20%. It doesn't matter what alpha is. 20% is not going to convince anybody. So we had something like a 20% chance of getting a 4.8 in the context that these folks believe is true. We had something like a 20% chance of our 4.8 happening. So that's not convincing anybody that this is wrong. These folks are, well, I think that's a perfectly everyday sample. I still think I'm right. Okay, so fail to reject. Okay, once again, emphasizing the fact that this is not really new stuff. That hypothesis test, we spent a long time on these H0s and HAs because this is the hard part. But we did it, it's done. Now we're reinforcing. You always say assume H0, you always find the sampling distribution, you always calculate the p-value as the shaded area. Every one of these, in this case we're doing means, every one of these has some slight twist. In the case of means, the slight twist is that if you're using S, you have to use the T curve. Okay, so a person practices some of them on the homework and gets better at them. But nonetheless, the basic idea, assume H0, find a sampling distribution, use that to calculate the p-value, and then either reject or fail to reject. That's the hard part, and that's all the same. Okay, all right, very good. So so that's the homework for section 6.2, the 3 sort of subsections for 6.2, and I hope everybody has a nice sort of Easter break, and I hope everybody stays well. We'll see you.